Hello.
Yes, yes.
Hello, sir. Right.
Yeah, we'll start in 2 minutes.
Okay. Okay.
So is my screen visible?
Yes, sir.
Okay. So let us start. So we'll begin with a very quick review of some of the concepts that you have studied as a part of network flows. And then we'll look at an application of network flows. Okay. So just to recall, in the network flow problem, the input is a directed graph G, a distinguished source vertex S, a distinguished sink vertex T, and our object, and each edge is associated with a capacity which is a non-negative integer. So we'll assume for the time being that all the edge capacities are non-negative integers, and our objective is to push as much flow as possible from the source to the sink across the graph. Okay, so objective is to maximize the amount of flow from S to T.
Sir, are there any edges that or any capacity coming into the source or going out of the sink?
No.
That's also possible?
No. So for the time being, we'll be assuming that no edge is entering into the source and no edge is leaving the sink. Okay.
Okay. And if let's say we have two vertices U and V, and there is an edge between from U to V, directed from U to V, can there be an edge from directed from V to U?
Well, it is possible. You
Okay.
can have such an edge. Yeah.
All right.
But okay, so you can you can have such kinds of edges.
Okay.
Yeah.
All right.
So our objective is then to push as much flow as possible from the source to the sink. So of course we need to define what this flow is. So flow is essentially a function f which satisfies two properties. The first is that for any edge, f of fe will be less than c of e. So c of e will be the capacity of the edge and fe is the flow on that edge. So basically you cannot push more than what the edge can carry. This is what it intuitively means for all e in E. And secondly, the total flow entering into any vertex is equal to the total flow leaving that vertex for all V in V, of course, except the source and the sink, okay, except S and T, right? So
Right.
under these constraints, we need to maximize the amount of flow from the source to the sink. So you might have studied the Ford-Fulkerson algorithm. Sir might have introduced the Ford-Fulkerson algorithm, right?
Right.
Right. Okay, so before we actually go there, we'll so now since so the object the way to go about it is very simple. You start with a feasible flow and then improve it successively. Okay, so you try to make some improvements in every iteration until you have finally attained the maximum flow. So now how do you make these improvements? So in order to make these improvements, we define two operations, or we basically rely on two operations. So operations for improving the flow. The first is that if at all an edge is not completely saturated, then there is still some scope of pushing additional flow across that edge, right? So if I can push additional flow across an edge, then I would always try to do that, right? So that will be the first operation. So push additional flow if edge isn't completely saturated or isn't saturated. And the second operation would be that if at all a particular edge is carrying some amount of flow, then I might want to undo some of the flow on that edge and reroute it in a different direction or reroute it along a different edge. Okay, so undo some amount of flow on an edge already carrying flow, already carrying it. Okay, so
Okay.
now both these operations can be abstracted out in terms of the residual network. So so given a flow F, given a flow F, we can construct a residual network GF as follows. So for each edge E, let's say its capacity is C. So, and let's say it's carrying a flow FE. So for this edge E, if FE is less than CE, it means I can push an additional CE minus FE units of flow across this edge. And therefore, I'll introduce a forward edge in this residual network from U to V, whose capacity will be CE minus FE. On the
Right.
other hand, if this edge is carrying some non-negative flow, then I can undo at most FE units of flow on this edge. Therefore, I'll introduce a backward arc in the residual network and its capacity, its residual capacity would be equal to the flow on the edge U. Okay. So
So,
basically, yeah.
would it be in principle possible that if there is some, uh, although there is no capacity for any edge going into the sink, but in the
Mhm.
residual network there would be, right? So we could uh, have some
Sorry.
flow.
Could you come again?
We wouldn't have any capacity for any edge going into the sink, right? Because that's a restriction that
Into the
on the graph.
sink.
Right. No, sorry, into the source.
Yeah.
Into the source, we don't have any edges, right?
Right.
So there is no capacity. But then in the residual network, it could be possible that there is some capacity for, like, I mean, even after the
I
first
mean,
step, that we would find an edge.
no. So are you saying that one of the edges which is leaving S would present itself as a backward arc in the
In the
residual
residual graph,
graph?
right?
No, how would that be possible?
So
Yeah,
because
I mean, yes. Of course, it's possible. Of course, yeah, uh, it's possible.
right, so we could in principle have an output flow where there is some flow entering the source as well, right?
Uh,
Eventually, when we run something like the fold person.
in some sense, you can say like that.
Okay. Okay.
Hmm. Yeah.
Got it.
Okay. Uh, right. So once we have defined this notion of residual network, and we use this residual network then to construct this flow, to basically find the maximum flow, to be more precise. So can you tell me what are the steps of the Ford-Fulkerson algorithm?
Right. So we firstly use, okay, the regular description of any iteration would be to find a path from S to T,
Hmm.
which we
In
would use a linear time algorithm for a graph traversal algorithm to do that.
Yeah, so so now here you are talking about, here you have two graphs, the original network and the residual network. So in which graph will you find the ST path?
Oh, well, we haven't really established any flow yet. So there is no residual network, right? This is the first iteration.
Yeah, so but then,
Okay,
okay,
if I'm saying
if
inductively,
you,
then we should always use the residual. And let's just say that the residual for the first step is the graph itself.
yeah, okay.
So whatever residual graph we have, we will just use a linear time graph traversal algorithm to find a path from S to T,
Hmm,
identify its bottleneck uh, edge
hmm,
in terms of the capacity, and flow that much flow in through that path, and then
hmm.
recalculate the next residual for our next iteration using that. And if we can't identify any path, then that means that we've ended the algorithm. The algorithm has to stop there.
Okay, right. So what you so basically, the first step, so as you said that in the first step you find the path, ST path in G. That's the same as assigning a flow value of 0 on every edge and then uh, constructing residual network out of it. So that will be the same thing, but just for for just to present it as a whole, we can start by assigning a flow value of 0 on every edge.
Okay,
Then
right.
uh, you construct the residual network, construct GF, then you find an ST path in GF, then you basically find the bottleneck edge, then augment along the ST path, and then again you repeat these steps until until there are no more ST paths in the residual network. Repeat until no more ST paths.
So you said
So
augment along ST path, right? That just means we just
yeah,
add the capacity to the flow.
yes, yeah. So
Uh,
you add the capacity, so you increase the value of the flow on the forward edges and decrease the value of the flow on the backward edges. Okay.
okay. So decrease the value of the flow or decrease the capacity? Oh, sorry, actually increase the capacity, right? increase the capacity along the backward edges or not?
No, you decrease the value of the flow on the backward edges and you increase the value of the flow on the forward edges.
Oh, okay. And we decrease the capacity on the forward edges and increase the capacity on the backward edges. So it's a dual operation in that sense, right?
No, why would you decrease the capacity?
Because
I mean, in the residual network, of the capacity automatically decreases, right? The moment you reduce the flow, the so the capacities, sorry, the moment you increase the flow, the capacity automatically decreases in the residual network, right? For any forward edge.
right. Okay. So when we increase the flow in the forward edges, you're saying we also have to decrease the flow on the backward edges, or isn't that something that already happens automatically? So if we were to talk about the flow from U to V, will we not be doing f of v comma u f of u comma v minus f of v comma u?
F of, just a second. So you have an edge UV,
Right.
sorry, UV. So it's carrying the flow FUV and its capacity is CUV.
Right.
Okay. So now you have, so it, there is, you have found a bottleneck edge to have capacity B. Okay. Now, so what you'll be doing is, if this edge is a forward edge, that means I can push at most B units of, I can push B units of flow further across this edge, right?
Right.
I can push an additional B units of flow across this edge.
Yes.
So I'll increase the value of the flow by B.
Right.
If at all it's a backward edge, that means I can undo that much flow, in the backward direction, right? Along that edge, along this edge.
If this is a backward edge in
In G.
okay.
In G.
Oh, okay. So you're saying that if, let's say, we've identified a path from S to T and it goes as S something something, then reaches V, then goes to U, then something something, and then T. If that is the setup, then we will be using UV as a backward edge, and hence we will decrease the flow FUV to FUV minus V.
So UV would be, so it depends. So UV need not necessarily be a backward edge, no? It could either be a forward edge or it could be a backward edge.
Right.
So it might so happen that the actual edge in G is from V to U. It's carrying some non-negative flow, as a result of which it has created a forward, an edge from U to V in the residual network.
Right.
Right. So that means, so this your UV edge, so U to V edge on the path P becomes actually, would be representative of a backward edge, no?
Right. It has both characteristics now. It is a backward edge as well as a forward edge.
Yeah,
right?
that is possible. It can be forward as well as backward.
Right.
Okay. I mean, the same edge can create a forward as well as a backward edge. That's what I'm saying. Okay, but when you talk about a path, your path is either going to use U to V or it's going to use V to U. It's not going to use both, no? Otherwise, it doesn't make sense.
Right.
So the edge is going to be either forward or backward, but
with respect to a path.
Yeah, with respect to your chosen path. But an edge in G could spawn both kinds of edges, forward as well as backward.
Right.
Okay.
Oh, okay. So what my doubt here is, let's say that after some iterations of this fruitful question, what we've obtained is we can just look at the edges U and V, and there are both a forward edge and a backward edge associated with it. They both have some flow going through them, and they both have some capacities to them, which are both not saturated capacities, let's say. So there is some FU so there is some positive FU comma V, and there is some positive F of V comma U as well.
Okay.
And this is possible in this algorithm, right? We could have such a stage.
I mean, so see your UV. Okay, so we are assuming the existence of both kinds of edges, no? In
Right,
G,
right.
so yeah, so that's possible. Okay, yeah.
Yeah, so I'm saying it's also possible that we have positive flow in both of these edges, right? At any point of this algorithm, after some many steps of this fourth Fulkerson algorithm, we could have a stage where there is some positive flow from U to V as well as some positive flow from V to V, right? Now, let's say we run an iteration and we find that the path that we found in Ford Fulkerson treats UV as a forward edge.
Okay.
And we want to push B more flow to it because there is some bottleneck B capacity edge further along this path, let's say. So what will be the augmenting step? We will be we definitely will increase f of u comma v to f of u comma v plus b, right?
Right.
Would we also decrease f of v comma u by b?
No, you shouldn't.
Okay, so we want, so the backward flow will be left untouched, and
right.
And the only difference is, the only update to the flow will be just how when we're treating it as a forward edge, we just increase its flow, and we just look at their capacities. Where the capacity of the forward edge would definitely decrease when we're calculating the residual.
Yeah.
And the capacity of the backward edge will increase, right?
Right. Yeah.
Okay. All right. Okay.
Right.
Okay.
So the so we continue augmentation until there are no more ST paths in the residual network. Okay. So what is the time complexity of this algorithm?
Right. So if we look at right, so we did this result that the minimum cut vertex of any residual graph is decreased by the amount of flow that we've added into it. And this is important because we want a bound on this, on the number of times we would want to do this linear time graph traversal, right? So we can't really bound that by just the number of runs, just by thinking that the number of paths is bounded or something, because even a single path can be visited many times in this algorithm. So we want to see if there is a monovariant in terms of the minimum cut vertex, and we showed that the minimum cut vertex in the graph is decreased in the residual graph by the amount of flow that we pass in every iteration. So the minimum, right?
What is the minimum cut vertex?
The minimum cut vertex. I'm sorry. Minimum cut set, not the minimum cut vertex. So minimum cut set is the same thing as just a set of edges. If we were to cut them out of the graph, then the graph will be disconnected in ST.
Okay, so first of all, okay, so instead of going to the max flow min cut, first of all, we have started with the assumption that all the edge capacities are integers, right?
Right.
Now, so in every iteration of Ford Fulkerson, the resulting flow values and so at the end of every iteration of Ford Fulkerson, the resulting capacities and the flow values that we get would also be integers.
Right.
Right. So that means, and you know that in each iteration of Ford Fulkerson, the value of your flow is going to increase.
Okay. Right.
Right. That means that means at the end of every iteration, the value of your flow increases by at least 1.
Okay. Right.
Correct. And yes, I know that the value of the flow cannot be more than this quantity.
Summation of capacities. Yes.
Right. So that means, and a single iteration of your Fortfull Curson is going to take order of V plus E time.
Right.
Okay, so that means your running time is bounded by this.
Or C times V plus E. Right.
Okay, so this is the complexity of your algorithm. Okay,
Okay. Right. And
right.
instead of C here, we could have just replaced it by any cut set, but we know that this is a trivial cut set that we can analyze.
Yeah, I mean, of course. So yes, of course. You could have replaced it with the capacity of any cut.
Right.
Yeah. Now, um, so as you've seen, so suppose F is any flow in G, any ST flow in G, and let us say that C denotes the capacity of any cut in G. Okay, C is the capacity of any cut in G. Then what can you say about the relationship between the value of the flow F and the capacity C?
That flow has to be lesser than equal to C.
Right. So in general, the value of any flow will be at most the capacity of any cut in the graph. So for instance, if I were to plot the values of possible flows in the graph and the capacities of different cuts in the same graph, then I would have all the values of the flow over here. And then I'll be having all possible capacities of the cut, capacities of cuts. So in principle, we know that the value of the maximum flow
It's lesser
is
than
at
equal to the
most
maximum.
the capacity of the minimum cut.
Right.
Right. So now, for a given flow F, if I'm able to exhibit a cut which has the same capacity as the value of the flow F, then I can very easily say that F is going to be my maximum flow and the cut AB, let's say the cut AB is my minimum cut, right?
Right. And that is where the equality is attained.
Right, exactly. So let us suppose that F is the cut returned by Fortfull Curson after termination.
So F is the flow returned by Fortfull Curson, right? Not the cut.
Right. No, flow. Sorry. Flow returned by Fortfull Curson after it terminates. Given this flow, how can you actually recover the min cut from the graph? So when does Fortfull Curson terminate? So F is the flow with which it terminates. That means if I construct the residual network with respect to the flow F, S and T there won't be any path between S and T in GF,
Right.
right?
So that means
That
that
means
when we
that
run the graph traversal on this, then we don't find any path.
yeah. So with S as the source, if I run breadth first search or depth first search, I won't be able to reach T. So I essentially have two connected components.
Okay.
So
Okay.
run BFS from S in GF. So let A be the set of all nodes which are reachable from S. So V reachable from S in GF, and B will be the rest of the nodes in GF. So first of all, AB is certainly an ST cut
Right.
in GF and also in G. Okay. Now, in order to show that this is indeed the min cut of G, what you need to do is simply show that the capacity of this cut is equal to the value of the flow F.
Right.
Right? So
Yes.
how do you show this? So consider an edge UV. So
the capacity of AB we're looking at in the original graph, right? This is not in the
yes,
residual.
yes. In the original graph. So let us consider an edge UV such that U is in A and V is in B. Okay. So UV is an edge in G, right? Now, suppose it is carrying flow equal to FE. Now, what can I now can so can FE be less than CE? By CE, I mean the capacity of this edge.
No, because then we've already identified a path from S to T, which includes UV.
Exactly. So if the flow on the edge UV is less than the capacity of this edge, then in the residual network, you'll end up getting a edge from U to V. You'll end up with an edge from U to V having some non-negative, not non-negative, positive residual capacity, which would then translate to a path from S to T in the residual network, which is a contradiction, right? Because
So, but
full question.
what if that path what if flow f of E is equal to 0? What if f of E equal to 0? Then do we know that there exists a path from S to T with the edge UV?
So, I'm sorry, could you please come again? I couldn't get it.
If f of E is equal to 0,
Hmm.
how do we know that there exists a path from S to T which includes UV?
If f of E is 0, but if there is no flow,
right,
from U to V, so could you repeat your question once again? So what you're saying is, if the flow on this edge is 0,
then how do we
how do
know
we know?
that there exists a path from S to T which includes this edge UV? Because we are using that path in our argument, right? That there exists a path from S to T which includes UV. Right? And then we can add some more flow.
So, see, if f of E, so see, if the flow on an edge is 0, why do I really care about it? First of all, I would so I'm always assuming that my flow is non-negative. So positive flow, because if the flow is 0, there isn't really anything to do, right?
Right.
So
Wait. So, but then, if the flow is 0 up till here, that means. Oh, so does that mean that there could not have been a path from? Actually, what if I'm saying that if there is a path from S to T which includes UV?
okay, just a second. So you have S T. Okay, so U V. So this is in
Right.
which network?
This is in the original graph.
This is in the original graph. Okay.
Right. But what if? Okay, let's say there is some flow in this which is lesser than CE. But there is some edge in this path from V to T, which has zero capacity in the residual, in the final residual.
There is some
edge in V to T. Yeah, there is some edge in this path, which has zero capacity in the residual.
Okay, so then basically you'll have a so then you consider a different edge, right? So instead of considering U to V, you would
Right.
consider maybe a different edge.
No, so but we're trying to contradict the existence of any edge with f of e is lesser than ce, right?
Okay,
We're trying
so
to
um, let's just first of all try to complete it and then we'll get to your doubt. Okay.
Oh, okay, right.
Okay. So so you have an edge from U to V in E. So with one endpoint in A, the other endpoint is in B. Okay. So by the way, the okay, so we'll get to that later. So suppose this edge is carrying a flow equal to Fe. Now, if at all Fe is less than Ce, then this edge is going to create a forward edge that goes from A to B in the residual network. And consequently, there'll be a path from S to T in GF, which would be a contradiction. Therefore, the flow Fe should be equal to C of E for all E equal to U comma V with U in A and V in B. Okay. Else.
So, but this thing is assuming that B is a connected component, right?
Assuming, yes, of course, B is a no. B is a connected component in GF.
Right. In GF, we are assuming that B. So let's say if we were to reverse the direction of every single vertex in B, sorry, every single edge in B, then we're saying that if we were to do a graph traversal algorithm from B, we would obtain the whole B, whole set B, right?
Right. Yeah.
At least the whole set B. So
Yeah.
that means, okay, so how do we firstly know that that is true?
Because when your Ford Fulkerson terminates, so see, the termination of your Ford Fulkerson is going to happen only when the ST path is when there is no longer any ST path in the residual network, right?
Right.
So as long as there is an ST path, I would be able to find an ST augmenting path in the residual network, no?
Right.
Okay, so that means, of course, now so we actually seek only for the components that are containing S in. So see, what is the graph in your GF in general doesn't necessarily have to be connected throughout the iteration. But as long as S and T remain in the same connected component, my residual network is always going to find some ST augmenting path, no?
Right.
Okay, but the moment S and T break into different connected components, I terminate.
Okay. Right.
Okay, so what I'm going to do in that case is the component containing S, all those vertices would form one side of the cut and everything else will be the other side of the cut.
Right. So would it not be okay? So it could be possible that in GF there are multiple connected components, right?
Yeah.
More than two.
Yes. In principle, that's possible.
So in that sense, we shouldn't be using U in A and V in B, right? Because V is just defined as V minus A. It should it not be defined as the connected component of the sink T?
No. Then you won't get a cut, no? For a cut to happen, you need a partition of the vertex. If you simply restrict to the connected component containing B, then you won't get a cut.
Okay. So I'm actually confused. Let's say there are three connected components. Let's call them A, B, and C. Oh, actually,
Hmm.
B is already. So let's call them A, C, and D.
Hmm.
All right. Where D is the connected component which contains the sink T,
Hmm.
and A is containing S. So what if we've shown that uh, there is some forward edge from A to C? So let's say E is an edge from A to C,
Hmm.
and f of E is lesser than CE.
Hmm.
But there are no forward edges from C to D.
Okay.
So here we are finding some forward edge from A to C, but that doesn't give us a path from S to T, right? So there is no contradiction in this case from uh, that f of E is lesser than CE. Because to obtain that contradiction, we required that if there is an forward edge from A to B, then there is a path from S to T. But here we don't have that path because C and D are disconnected, right?
Hmm.
So doesn't the argument not work then? Because we have multiple connected components, more than two.
But okay, wait a minute. But the moment S and T get disconnected, you would
Right.
have so see the moment S and T get disconnected. So okay, I'm actually not able to say it, but see the moment your S and T, we are actually looking at that point specifically where the S and T get disconnected. We are
Right.
we are focusing only on that point. So so we are essentially looking at only that situation where S and T are going to get disconnected, not anything else. Okay.
Right. So by this point, we could have already made some connected component C which does not contain either of them, right? Which, as you said, we could have already created a disconnected component
Yeah.
by the point that we
Yes.
we
So in
disconnect
that
these two.
case, yeah. So see, the choice of edge is finally with me. Which edge to choose, that is again my choice. So as you said, there could possibly have been edge from some A to C which doesn't contain T, but then I could have chosen an edge that goes from component containing A to the component containing T, right?
But we're okay. So, but then that does mean that the result that we are trying to prove is to say that for any edge from the connected component of S to the connected component of T will have flow equal to capacity, right? That is what the result would be in that case, right?
Yeah. So yeah. So could you please repeat again?
So I'm saying then if you're only considering those edges which are
Hmm.
going from the connected component of S to the connected component of T in the residual graph,
Hmm.
then the result will have to be reframed, right? Because then what we are saying is consider any u comma v belonging to E such that u belongs to A and v belongs to the connected component of T and not just any vertex in the remaining vertices, right? Then we know that f of E is equal to CE from this argument at least.
Mm, I'll have to think about it. Okay, I'll get back to you, but I'll think about it and let you know.
Okay. Okay. So for
Okay.
now, are we assuming that this statement is true for any vertex outside A for the whole of set B?
So for the time being, let's just assume that it is true for whole of the set B.
Okay. Okay.
Uh, yeah, but I'll get back to you. Okay.
Okay. Okay.
Yeah. So um, where were we? So if the flow carried is less than the capacity of this edge, so then I'll be able to create a forward edge, which would give me a path from S to T. And what about the, suppose now there is an edge that goes from, that has its head pointing in A and its tail in B. For any such edge, your flow must be 0, because that is, such edges should not carry any flow. Because if they were, then I would have because if there was some non-negative flow, then there would have been a backward edge in your residual network. Okay, that carries some positive flow.
So then what if there is some backward flow as well as some forward flow?
Sorry?
So what if then there is some flow from B to A? And that means that there is a forward edge capacity from A to B. But then there is some forward flow in that or along that edge as well. And so that capacity is reduced to 0 again.
Okay, no, can you please come again? So there is this, so this is carrying some non-negative flow, okay, positive flow, then?
Okay, yeah, right. So let's say that U and V are two, right? So U and V are already named, right? So let's say that capacity of U comma V was something positive in the original graph. And there is flow running of the value C of, oh, okay. Sorry. I understood my mistake.
Okay. So, okay, so that means when your Ford Fulkerson algorithm terminates, then all the edges going from A to B in G would be completely saturated, and the ones which are going from B into A would carry 0 flow. So if you compute the value of the flow, so the value of the flow is essentially this. Now, F out of A is going to be the capacity of the cut AB, and this is going to be 0. Okay, so that means given this flow, we have exhibited a cut whose capacity is the same as the value of this flow. So therefore, your cut is indeed a min cut. Okay.
Okay. Right.
Yeah. Okay.
So this is also
okay,
a result that we're using, right? That value of a flow across any. So value of a flow can be expressed that as f out of A minus Fn of A.
Yes. So this result, I hope this must be. Is this done? Have you seen this result?
Yes, sir. Right. We have seen this. Yes.
Yeah.
In the last semester.
Okay. So you can use this result. It comes in quite handy. So, okay, let me directly move to the application of, let's look at an application of this network flows. So the input is a directed graph with a distinguished source and sink, and our objective is to find the maximum number of edge disjoint paths in G. Okay, so edge disjoint ST paths in G. Okay,
edge disjoint. Okay, right.
Yeah. So first, how will you model this problem as a network flow problem? So So what we can, so we'll set the source vertex as S, the sink vertex as T, and let us set the capacity of each edge in G to be 1. Okay.
Right.
Now, given this flow network, so
Right.
okay, now suppose I tell you that there are k edge disjoint paths from S to T in this network.
Okay.
Then can you say that the maximum flow in this network is at least k?
Right.
Right? You simply assign a flow value equal to 1 for every edge on each of these k edge disjoint paths, and you immediately exhibit a feasible flow of value k.
Right.
Therefore, maximum flow is going to have value at least k.
Right.
Okay. So if G has k edge disjoint paths, then max flow value is at least k.
Yes.
Now, suppose we can show that even the converse of the statement is true. Okay, that is, given a directed graph, if the value of its value of flow in that graph is at least k, then it contains k edge disjoint paths. If I could somehow show this, then this problem essentially reduces to a max flow computation in G.
Right.
Right?
Right. Then we would have modeled this problem as a network flow problem. Right.
Oh, right.
Right.
So
Right.
let us try to prove the converse. So
Okay.
if G has flow of value at least k, then G contains k edge disjoint paths. Okay. Now this is where we use uh, the integrality theorem that you have studied. So here in G, every edge has capacity 1, right? So basically
Right.
all edges have integer capacities. Therefore, it is possible to exhibit an integer flow of value k in this network, right?
Right.
Okay. So
Mhm.
let F be an integral flow.
Because we know that full fold frequency on this would definitely give us an integral flow, and it will also give us the maximum flow. So it has to be a an integral flow which is greater than equal to k.
Yeah.
Okay.
Okay. So suppose F is an integral flow for G. Now, in order to show this statement, we'll be using induction on induct on the number of edges carrying unit flow.
Oh, okay.
Okay.
Right.
So this is actually the crucial point why we need this integrality, because the capacities are so the capacity of every edge is 1. If F is integral, it's going to assign an integer valued flow for every edge, and since the flow value cannot exceed the capacity, each edge either carries 0 flow or it carries a unit flow. Okay. So if we simply restrict ourselves to the subset of edges which carry unit flow, then using this subset of edges, or rather within this subset of edges, we'll find our k edge disjoint paths. Okay. And in
Okay.
order to recover those paths, we are essentially using induction.
Okay.
So let
Okay.
uh,
So just I had a doubt.
yeah.
1 and 0 flow is fine, but can we also think of -1 flow in the sense that there could be flow in the reverse direction of an edge?
Flow values can never be negative, no?
Right, but then if you want to talk about the flow from some vertex u to v, And what if there is some flow from V to U? Would we consider that as a completely different edge?
No, but um, so basically you're talking about the presence of the edge UV and VU and G. Is that what you're
Right,
saying?
right,
So
right.
no, in this case, we'll be assuming that either one of the two are there, not both.
Oh, okay, okay.
Okay.
And so this is not an undirected graph. This is a directed graph, and every edge has a single direction. It can't have both directions.
Yes, yes.
Okay, okay.
Yeah. Okay. So, uh, right. So, so let V be the value of the flow of this. Okay. So we have already assumed K to be the value. So let's not now. So let us suppose that K is non-zero. Okay.
Okay.
Now that means there must be at least one edge carrying unit flow which leaves the source vertex.
Right.
So let's call that edge SU, carrying unit flow. Now again, for the conservation constraints to be satisfied, there must be at least one edge which
Coming out of U.
leaves you carrying unit flow.
Right.
So let's call that edge UW. So it's also carrying unit flow. So
Right.
continue this process.
We have to
Now,
under T because of conservation.
yeah, so at this point, so if you continue, you would end up in either one of the two situations. Either you visit T or reach T, or you visit a node that you have already seen before on this path.
Okay. Right.
Or visit a node again on this path. So let's call that node V. Okay.
Okay.
Now let us consider the first case. So in the first case, you reach T. So that means you've already found your ST path, one of your ST paths. Okay.
Right.
So you record that path and now simply decrease the value of the flow on the edges of this path by 1. So you are essentially reducing the flow values on each edge of this path to 0. Okay. So decrease FE to 0 for all E on this path.
So which path are we? If this is when we've reached T. Okay.
Yeah, when you reach T. Now, when you do this, you have essentially decreased the value of your flow from K to K minus 1.
Right.
Okay. So your value of flow has reduced to K minus 1. Value of flow reduced to K minus 1. And now you have fewer edges which are actually carrying the flow.
Right.
So now you can use your induction hypothesis to come up with the remaining K minus 1 edge disjoint paths.
Oh, and they'll be disjoint because we've just removed these edges from this graph altogether. Okay. Right.
Okay. Now,
So edge
similarly,
disjoint means edge disjoint paths means they don't share an edge, but they can share a vertex, right? That's not a problem.
yeah, that's not a problem.
Okay. Right.
Now, consider the second case when. So now look at the cycle. Let's see be the cycle between consecutive appearances of the vertex V.
V. Right.
Yeah, consecutive occurrences of V. Now, what you do is simply reduce the flow value on every edge of this cycle to 0.
Okay.
Reduce FE to 0 for all E on this cycle. Now, doing this operation, does this have any effect on the value of the flow in general?
No, because we haven't reduced any flow coming out of S or going into T.
Right. So the resulting flow continues to be V, resulting flow V, but now you have fewer edges carrying your unit flow than what you started with.
Oh, so we're not even inducing on K. We're just inducing on the number of edges.
Yeah. We are inducting on the number of edges carrying the flow.
Carrying the flow. Okay. Right.
Okay. So the resulting flow continues to be continues to remain K. So by induction hypothesis, you get your K edge disjoint paths in G.
Okay, so we're inducing on the number of edges, and we're saying that if there is a K flow, we can divide this K flow into disjoint K paths.
Yeah.
Okay, got it.
Okay. So what we have essentially shown is that there are K edge disjoint paths in a directed graph from S to T only if the value of the maximum ST flow in G is at least K.
Got it.
Okay.
If and only if.
Yeah, if and only if statement, kind of statement.
Got it.
Right? So now all you need to do is to simply compute the maximum flow.
Got it.
Make sense? Okay. So
Oh,
I'm
wow.
going to give you.
This gives us a way to just calculate the maximum matching as well, right? Or no.
No.
No, sorry.
Okay. So now I'm going to give you two problems as your homework. Try them out. The first one is actually a direct consequence of what we just did. So, find a minimum subset of edges F that separates S and T in a directed graph G. Okay, so G is a directed graph. Again, S and T are distinguished vertices. You want to find a subset of edges that separates S and T, which means that if you remove the edges in F from the graph, you end up with S and T in two different components. Okay, there won't be any way of getting from S to T. So you want to find the minimum such subset of edges.
So, but then isn't that the same as asking what the minimum cut is?
To a certain extent, yeah. So it's just a reformulation of the previous problem.
Okay, so the answer would be just running at for question, right? And then just using a BFS on S.
Right. So basically, this is equivalent to saying that the maximum number of edge disjoint paths in G is equal to the minimum number of edges needed to separate S and T. Okay, just so this is in terms of what we just did. Okay, and it's not very difficult to prove it using this max flow min cut framework that we have seen just now. Okay. So the maximum number of edge disjoint paths from S to T in a, okay, so this is ST paths, okay, by the way. The maximum number of edge disjoint ST paths in a directed graph G is equal to the minimum number of edges needed to separate S and T in G. Okay. So do you know what this is called? This is, have you heard of Menger's theorem?
No, sir.
No? Okay. So this is called Menger's theorem.
Maybe I think it was mentioned in the previous semester, but I can't recall it.
Okay. That's fine. So this is called the Menger's theorem. If you look at the classic proof of Menger's theorem, it's very long. As opposed to that, this is a relatively simple proof of Menger's theorem.
Okay, so we just took the LHS, proved that it is maximum flow. We took the RHS, proved that it was maximum flow.
Sort of.
Actually, in the right hand side we proved it to be maximum flow, and left hand side we proved it to be maximum integer flow, right? And then we showed that maximum flow is equal to maximum integer flow using Ford.
Yeah, I mean, I think you could extend the same integral flow even to this minimum subset of edges thing, no? You should be able to extend it to the same question. It basically depends on how you model your graph or your flow network.
Right. Because we actually, to prove that min cut is equal to max flow, we definitely did use the integer flow in any case, because we just proved that using the Ford-Fulkerson.
No. See, max flow min cut theorem doesn't really impose any constraints on your flow being integral. Okay. The max flow min cut theorem will hold even if your flow is not integral.
Right.
Okay. So what does the integrality theorem states? It basically states that if the value of the flow is k, if all the capacities are integers, then there is a flow which you can exhibit a flow with that value. It doesn't say that every flow is going to be an integral flow.
Right.
Okay.
Right.
So max flow min cut theorem doesn't really say that your flow has to be an integral flow. It can be any flow.
Right.
Any kind of flow. Okay. Right.
Okay.
So this is one question. Try it out, and second, try to extend what we did here. That is, try to extend this to undirected graphs.
To undirected.
Extend the problem to undirected graphs.
The first problem. Right?
Yeah.
With the Menger's theorem to undirected. Okay.
Yeah. Now, and just the last question. So let G be a network, so it's a directed graph. So it's a flow network, basically. Flow network with unit edge capacities.
A flow network means that function has already been identified, the flow function.
Yes, a flow is given to you.
Okay.
The distance between S and T cannot be greater than 2 times the number of edges divided by value of f hat, where
So 2 times number of edges, or what is it?
vertices, sorry, where f hat is the maximum flow in G. Prove it. Okay.
So the distance is just the regular distance with no weights, right?
Yeah.
Okay.
Yes, it's the number of edges, not the weighted distance.
Right.
Okay. So try to do these questions, and I will get back to you regarding this. Okay. Let me think about it.
Okay.
So do you have any questions?
Sir, I had a question from our discussions on the minimum spanning tree, which is okay. It could be quite a digression. So should I ask?
Uh, Drop me a mail. I'll take a look at it and get back to you. Or we can maybe schedule some discussion on it later.
Okay. All right.
Okay.